both these learnings have one significant disadvantage. The disadvantage is, and this will take you some time to recognize the beauty of, the disadvantage is that they are looking for one Bayesian network that best fits the data. Suppose there are 3 Bayesian networks. This has probability 0.3, this has probability 0.3, this has probability 0.4. Let us say this is first, second and third. First and third have probability 0.3 each and the second has probability 0.4. Which Bayesian network will be picked? Bayesian network number 2. I will find one set of parameters that are the best and that Bayesian network will become my model. An alternative way to handle this would be, do not pick a Bayesian network. Maintain all these 3 Bayesian networks in as possible hypotheses. And then if you are given a query, like tell me probability of A given B or whatever, anything like this, I do it based on all 3 Bayesian networks and then I give you the best value. For example, if probability of A given B was false, was 0 by Bayesian network 1, but it was 0 by Bayesian network 3, but it was 1 by Bayesian network 2. Then if I only pick Bayesian network 2, then probability of A given B will be 1. But when I kept all 3 in my system and then tried to estimate A given B, it will turn out to be 0.4. This kind of approach, where I do not find the best set of parameters, but maintain the full probability distribution over the set of parameters, this is called Bayesian learning. Okay? And this was the rage in the 2000s for theoreticians. The AI theoreticians, the probability theoreticians would absolutely love Bayesian learning because actually this is the best we can do given any kind of data. And to understand this, let us look at this particular example. Let us say there are 5 kinds of bags. Think of them as hypotheses. One bag has 100% cherry, the red candies. Some bags have 100% lime, the green candies. Other bags have 75-25, 50-50 and 25-75 split. Let us say I have only 10% of the first bag, 10% of the fifth bag, 20% of the second and fourth bag and 40% of the third bag. Now, I give you a bag and you start to draw out candies and you say, oh, green, oh, another green, oh, another green. I give you 10 greens. The question that you ask is, what kind of bag is it? And what flavor will be the next candy? Okay, this is my question. Now, notice that what kind of bag is it? It is a learning question. I gave you 5 hypotheses, 5 models of the world and I said I gave you some data from that distribution. Now, based on that data you figure out which model of the world you are in, that is the learning problem. Given the model, you figure out which flavor the candy would be, that is the inference problem, the next candy. This is called full Bayesian learning. We view learning as a Bayesian update of the probability distribution over the hypothesis space. I do not output one set of parameters as the best, I output a full probability distribution over the parameter space. So, a given set of parameter is a hypothesis. Think of this hypothesis as a random variable and that random variable is generating the parameters. And if I give you the full set of parameters, that becomes one model, one Bayesian network on which you can do inference. So, you can actually model a meta Bayesian network for a Bayesian network learning problem, where I have a random variable which is a set of hypotheses. And this D1 is the probability of generating the data given the specific hypothesis. So, H is the hypothesis variable, its value is H1, H2, Hn are sort of determining which Bayesian network was a priori more probable. In this case, those probability values will be 10%, 20%, 40%, 20% and 10%. The jth observation dj will be the outcome of the random variable dj in the training data d, right. So, dj here will be green for everything, right. And given the data so far, each hypothesis will have a posterior probability. So, that would be probability of hypothesis given the data. You can write it down as probability of data given hypothesis into probability of hypothesis. That is the a posteriori estimation. Now, if I take a maximum over all hypotheses, that is MAP. But if I do not take a maximum, and when I am asked a query like probability of x given d or probability that the next candy would be green given that I have seen 10 candies, I do a summation over this hidden variable h, which is the summation over all possible hypotheses. If I do this, that is called Bayesian learning, full Bayesian learning. That is, we do not pick one best guess hypothesis, we maintain the full hypothesis distribution in my space. And if you compute this, this will not be very complicated for you, you can try it out. So, initially if I have seen nothing, the estimates are 0.4, 0.2, 0.2 and 0, and 0.1, 0.1. As soon as I see one green candy, which hypothesis is just not possible anymore? H1 is just not possible anymore. And notice that its probability goes down to 0. The probabilities of H2, probability of H2 starts to go down, probability of H3, H4, H5 also start to vary. But over time, as I have only seen the green candies, you notice that all other probabilities go down to 0 and only the blue one, which is H5, that remains and becomes highest. Now, given this probability distribution of the hypotheses, if I am asked what is the probability of the next candy, I can do sum over these probabilities where all these 3 would be very close to 0, this would be 0.1 and this would be very close to 0.9, and that probability will turn out to be very close to 1. You can prove that if I give you some data, then Bayesian learning is optimal. This is the best you can do, you cannot do anything better than this. However, is it going to be practical? If I give you a structure and I want you to estimate probabilities, then you will have to maintain probability distribution over the probability space. If I have n probabilities to estimate, then you will be representing a probability distribution over n continuous variables. That will be very difficult to estimate. So, in practice, full Bayesian learning in a Bayesian network parameter estimation setting is not tractable and nobody does that. But theoreticians love to do it because that is the optimal thing, and they loved to find specific cases where you can make this tractable. Okay. So, this is called Bayesian learning. So, what have we learned so far in this class? We have talked about maximum likelihood estimation, we have talked about maximum a posteriori estimation that allows us to give some insight about which parameter is more likely or less, but they still compute one set of parameters, which is my model. Then I maintain the full model space, and that is called Bayesian learning. Okay. Bayesian learning is not to be confused with Bayesian inference and stuff. Bayesian learning means this very specific thing, right.